All right, the recorder is on. Got the mic going. All right, so let's go ahead and get started. We are already 2 minutes, past 1:30. What we'll do today is we are starting a new topic, and the new topic is pre and post conditions. This is probably by far the most difficult part of this class. Okay, and it might have to do with the way I teach it. It might have to do with the material. So there are many factors that may contribute to why this is the most difficult part of this class. So it would definitely be helpful if you can read ahead of the class, of at least the material, at least to get an understanding of what it is about. Okay, so in other words, if you look at the whole computer science program as a forest, this is basically, it's good to know where this tree fits in the forest. Okay, I won't expect you guys to focus on the needles, okay, because that's my job to introduce the needles and explain, how each one works and how they attach to the branches and stuff and so on. But understanding, why we have that tree in the forest is important. So we'll go ahead and get started with this. And there are three versions of this. I would not use the middle one. The middle one is generated like a long time ago. So some of it may not render nice, on a modern browser. PDF is PDF. There's not much to say about it. And the last one is the one that I would use if you want to open the document as an HTML document. I believe all of my documents are fairly friendly, even on a smaller mobile device like a phone, because it doesn't have a lot of fancy formatting or graphics or anything like that. It's mostly really just text and math equations. So you should be able to read most of this material on a tablet or even on a phone. May not be the best way to do it, but if you have a phone and you got a few minutes, you're waiting for a bus, that's one great way to just kind of get a little bit of material in. And if you look at the section 2, just the title of section 2, that might make certain people nervous. What is this crazy math? Okay. Not too long ago, we are talking about maybe the 60s or the 70s, which to some of you is a really long time ago, because that's way before you were born. Okay, that's when your parents were born. And I'm probably not inaccurate in that assessment either. Okay, but in the grand scheme of things, it's not really that long ago. Okay, so we'll go ahead and read this section a little bit. I'm not going to read it, but I'm just going to point out the sentences. So there are two schools of thought regarding how math fits into computer science, which is really kind of the other way around, because computer science is a branch of mathematics. Now, believe it or not, that really is the case. If you look at how computer science become its own department in most four-year universities, it either comes from engineering or it comes from mathematics. In other words, computer science as a department does not come into existence on its own. It is usually, from math. In other words, a whole bunch of math professors were teaching, things that are related to computers and programming, and then eventually, they just teach programming, and then, computer science becomes its own department. So that's coming from the software perspective, or the mathematical theoretical perspective. Or it can come from electrical engineering, where it is coming from the perspective of hardware. So electrical engineers and computer engineers, those are the people who make the devices. They are the ones who make the actual thing that can do computation. So naturally, some of those people would also be doing some of the programming, right? To specify what that computer should be doing. And eventually, those people specialized and become computer science professors. Is that okay? It is very unusual for a four-year university to have a computer science department that is a spin-off from business, which is the case here. Now that is kind of like it's not odd in the case of a community college, because in a community college, business teaches what? Originally, they teach people how to use typewriters, how to use those really big, clunky mechanical calculators and so on, because that's what you need in order to keep track of expenses and whatnot and type letters, in the good old days. Do we still use calculators that has a long crank and big huge clunky buttons? No. What do we do now? What do we use for calculations? Computers, and specifically what type of program do we use for calculations? I have used that quite often in this class. A spreadsheet. Very good. Okay, a spreadsheet. And the concept of a spreadsheet came about in, I would say, the late 70s or early 80s-ish. So it has been around for a long time. Do we still use typewriters? No, not even those kind of electric typewriters where you don't have to really push the key hard. We don't even use those, right? So when you have a paper to write in English Writing 300, what do you use if you don't use a typewriter? You use a computer, you use a word processor, okay? So Microsoft Word is a word processor. So is Google Documents, it is also a word processor. So we are even migrating away from computers, because your phone can run Google Doc just like your computer can, because it's really just it's not heavy duty on the client side, it's heavy duty on the cloud side. Okay, so and that's why computer science in this particular setting is a quote unquote spin off from business. Yep. Yes, it's a good reminder, but I'm pretty sure it's running. So let me just double check. Yep, it is running and it's connected and it's streaming right now. All right, so getting back here. But when you look at four-year universities, it's usually pretty math-based. Okay. All right. So within that context, modern day, wise, there are two giants in computer science. Two people who contributed a lot to current, computer science, concepts and programming ideas and whatnot. One person is Dijkstra. So he's a European. So there you go. This is his name, Esger Dijkstra. So he is the one who basically says you cannot be programming until you become proficient with mathematics. That is his view of things. Yes?
So in like computer programming, computer like science, we're gonna like while we're programming, or say like in future class we're gonna have to do like mathematical equations, or is that just like or it's just related to it?
Okay, that's a good question. So the question is, do we need to do math equations, or do we need to do calculus, before we program, or when we are writing programs? That actually is not the case. So mathematics has many branches. One branch that you guys know already is calculus. Okay, algebra leads to calculus, and then there's also trigonometry and stuff like that. Those are all things that are really useful. It trains your critical thinking, but they are not directly related to programming. What is directly related to programming is what we call discrete structure, and that's CISP 440 here. If you want to get a computer science degree to transfer to a four-year university, you will have to take that class. And that's mostly just a mathematics class. It talks about logic. It talks about combinatorics, the concept of combinations versus permutations. They talk about probabilities, like binomial distribution, and a few other types of distributions, probability distributions. And those are all related to computer science in one way or another. Okay. But getting back to this guy, okay, so he thinks that everybody should become a mathematician first, then you specialize in programming. So programming or computer science is a specialized area within mathematics. The second person who is also very important in computer science is Donald Knuth. He is still alive. He used to be a professor at Stanford University. So that's not too far from here, right? It's in Palo Alto. He wrote a lot of books on computer science, And he's recognized for many achievements, including the program that I use to generate all of these pages. It's called LaTeX, LaTeX, but it's really not LaTeX. It's more like LA, which is from the English alphabet, but it's tau epsilon chi. So you can look it up, okay? LaTeX. It's a typesetting program, and Knuth basically wrote that whole thing for himself so that he can use it to typeset his notes and publications in mathematics. So it's called LaTeX typesetting. So this will give me the correct context. So when you look at, when you click on this link here, it will explain what it is, the LaTeX project, and it's not pronounced latex because the first two letters are in fact the initials of a person, so that's in English alphabet, but the TEX, what we see as TEX, are actually tau epsilon chi in Greek, and I think it means text or something like that. You have to read the rest to find out what it is. But anyway, that's one of the achievements of Donald Knuth. And now I'm losing track of where I am. Well, I can just click here. Okay. So that's Donald Knuth. He is also very important in computer science, but his view is a little bit different. He's basically thinking with better tools, everybody can program. You do not need to have a math degree first to learn how to program. Is that okay? So you can see that they're holding opposite views. One guy is saying, okay, you have to be a master of mathematics first, then you can start to specialize in programming. And the other person is saying, well, with tools that we have now, you don't really need to learn that much mathematics, and you can just kind of get into programming because the tools are now much better than before. So you guys might have a question of, so what is he talking about? What kind of tools are we talking about when we are programming? Now in this class, I don't actually use a particular programming language, so we don't use any tools other than a spreadsheet, which I use as a big huge table so that we can keep track of the execution of a program manually, right? So you might want to ask a question of, but then how do we program computers in the past, in the good old days? So what we do is we can look up an older computer, and I cannot remember the name of that computer. Well, let's just look up old computers and images. And I'll bet I will find it within the first few pages. This is actually a good one too, but that's not what I had in mind. Nope, they don't have that here. Well, in the absence of that, let's take a look at this one here. And we just want to look at the image. Okay. Do you see a keyboard anywhere here? No. Do you see a mouse? Do you see a screen? Do you see any user interface whatsoever? No. So this computer is programmable by rewiring it. When I said rewiring, I really literally means disconnecting a wire, reconnecting a wire, disconnecting a wire, reconnecting a wire. The wiring of this computer is the only way you can specify what this computer is going to do. So writing a program on this computer is not going to be easy. Okay, does it make sense? Okay. Okay, let's close this image. What about the purpose of the original computer? Well, not the original computer, but the one at the end of World War II. The bomb, the B-O-M-B-E. So for those of you who have watched an imitation game, Can you recall what that computer was for? Yes. Oh, I thought you were answering the question. Yeah, go ahead. It's for cracking the encryption. It's for cracking the encryption that the Germans were using at the time, so that the Allies could could decode the messages, which is of huge advantage, right? If you just kind of think about it, if you can read all the messages from your enemy, doesn't that give you an advantage? Even if your forces is not superior, even if you don't have as much resources as the other side, if you know when they are going to where with how much troop and what their objective is, doesn't that help you to utilize your resources really well? Well, that's part of the reason why the Allies won. Because they were able to decode every single message that that the field German army was using, and also the Navy and also the Air Force. They can decode it as quickly as the Germans, if not faster. Now, how can it be faster? It's because when the Germans decoded, it was manual. In other words, the Germans would do it this way. They would receive the code, which is basically encoded. It would just be some garbled collection of letters. So somebody has to write that down and then pass it on to somebody else who's going to punch that into the Enigma machine. And then the Enigma machine will output the correct sequence of the code, and then you can read the message. The Allies, on the other hand, had a bomb computer. The whole thing is automated. So it is not uncommon for the Allies to be able to actually read the entire message before the Germans could, which is very ironic and funny if you think about it. And that whole thing is mathematics. It's all based on math. The whole science of trying to crack an encryption is a mathematical puzzle. Okay? So computer science has always have a mathematical basis. The only question is, how much math do you need to know in order to write programs? Okay? And absolutely, we have much better tools than even 5 years ago or 10 years ago. The tools that I'm used to is considered archaic by today's standard, but I still use it. Okay? So if you type your program in JavaScript using the right kind of editor, you can be typing half of a sentence, and then it will auto-complete the rest for you. Or at least it will give you suggestions of, oh, I think you might be just trying to specify this. So it doesn't put as much burden on your part anymore. Are you guys kind of getting the idea how tools are going to help you? Yep.
So if computers keep moving towards this, right, and they keep getting better and better, when it gets to the point where it just automate itself, and
well, if you think about machine learning, don't you think that's going to be the next step? Okay, so how many people here have heard of machine learning? Okay, most of you have. Okay, that's encouraging. And how does that tie into AI or artificial intelligence? What kind of machine learning have you been exposed to? Robotics, okay, that's one. But your phone probably has a few features that is based on machine learning already. How do you unlock your phone? Depends on, if you have a newer phone, you can use your face to unlock your phone. And how does the computer know, how does your phone know, what you look like? But it's machine learning. Because if you think about it, you can say, okay, my phone can take a few pictures of me, right? But what if the lighting changes? Okay, what if you have a haircut? Well, it measures features of your face. It learns from that. Okay, so in a way, it is machine learning. You can talk to your phone, right? Using Siri or Google Voice Assistant. And how do you think your computer knows what you're talking about? That's also machine learning. Okay, it's just going through a lot of samples of, this is the audio, recording of these words. This is the audio recording of those words. This is the audio recording of these words, and so on. So thousands, tens, and hundreds of thousands of samples would go through the computer, and then eventually the computer learns and understand that, oh, so this kind of sound means is this word. This kind of sound is that word, and so on. It can learn all that stuff. What else do you think computers can learn? Facial expression. Now, I'm not talking about facial recognition. I'm talking about expression recognition, like whether you're happy or sad. And you might think, okay, maybe it would take like thousands and thousands of samples, and it will need, a huge computer in the cloud to do it. That is not the case. I went to SF Hacks, which is a hackathon last year, and one of the teams, was using a laptop computer, and they were programming an embedded, an embedded application to recognize the face. So if the computer using a camera sees a person being sad or something, it would actually recognize that person is sad. Okay, and that was done in a day. It was done in a day by a student team in a hackathon activity. So we are talking about machine learning as if it is just a screwdriver today. It's a very common tool. Just about everybody has access to it and can get it to work to a certain degree to solve some problems. Okay? So if you are not yet shaking in your boots or shoes or sandals, you really should think about this, okay? Because if machine learning becomes more and more mature and computers are becoming more and more capable, at some point, it may not need programmers anymore. Think about what is the whole purpose of programming a computer? You're trying to get the computer to do something, right? What if the computer can learn that by itself? Do you still need programmers? So that's kind of a question I want you guys to explore and at least think about, because we are getting to a point where computers can start to reason. Okay. So this kind of material is not in the notes, but I think it is relevant because I really want you guys to start to think about these things. So if you look into IBM's Watson, okay, we talked about this in the personality test thing. But Watson can do a lot of interesting things. One of the things that it did was to play in the Jeopardy game. Now, if you're kind of older like me, you know what Jeopardy is. But if you're really, if you're in the newer generation, you may not even know what it is. So, I can just play the video without the audio because it doesn't really matter. But I can turn on closed captioning. Yep. So is there still closed captioning? Yep, there we go. So Watson is able to learn to the point that it can learn enough knowledge and it can apply what it has learned to win Jeopardy against expert humans. We are not talking about amateur people, that you just kind of take someone off the street and go like, okay, I want you to compete with my computer. No, we are talking about champions. And the computer was able to beat the champions. And all that time, the computer was offline. It was not able to, I'm just going to Google search for the answer really, really fast, right? Nope, it was offline the entire time. So are you starting to get the idea of what computers can do and what they can learn now? Okay? But there are things that we also want computers to be able to do that they cannot quite do yet, but I think they may be able to do it in the near future. How many people have taken at least one math class like algebra, trigonometry, pre-calc, or something like that? Okay, so you guys are kind of, you understand what a proof is, right, in mathematics, okay? It can be very simple. It can be just like, okay, prove that x equals to this number given this is the equation. Okay, it can be something like that in algebra. In calculus, it can be a little bit more involved, right? You can say, okay, what is the closed form of this integration, and so on. Okay, so what we're going to talk about in this class has to do with proving too. So I'll give you a few more interesting slides, to relate back to what we are going to talk about, in today's lecture. What are the bugs or the okay, heart bleed bug or attack? Okay. How many people have heard of this one? Okay, one. Very good. Did you take a security class? Okay, so that's probably why. Do you want to talk about it, or it's up to you? Okay, so the heart bleed bug. Okay, the term heart bleed actually is a play of the word heartbeat. Okay, so originally, there's a heartbeat, quote unquote, heartbeat mechanism in the SSL library implementation, which allows an outside entity to check and say, okay, are you still alive? Okay, are you still ticking? Okay, so it wasn't a very important function or feature of an SSL enabled server, but because there was a bug in the implementation, so when the people wrote the program, they wrote a bug into the program, and the hackers were able to utilize the heartbeat mechanism to crack the encryption of an SSL encrypted website. Okay, so you have to read the details to find out exactly how that happens. But the bottom line is it was because of a flaw in the program that we have a huge security risk exposure, and that's why it got kind of infamous. Is that okay? All right. So bugs happens all the time, because it's written by people. Okay, but the consequence of these bugs, the security consequence of these bugs, is becoming more and more and more important, because it can impact us in more ways, and there are also going to be immediate impacts as well. So we'll roll back the clock, okay, back to the 70s and 80s again. What do you think computers were used for in those days? Let's say in the 70s. That's before Apple II computers, before IBM PCs and whatnot. So what do you think computers were used back in the 70s? Well, they were used for sensors. Go ahead. Memory. But what are the applications? Well, they can crank out social security checks, right? Paychecks for for state employees. They can calculate your taxes and so on and so forth. Okay, so those are some pretty classic examples of how people use computers and still use computers for. Okay, so let's say there's a bug. Okay, somebody calculated your social security check wrong. Okay, and you're getting less money than you should. Is that a big impact? Yes, but is it correctable? Yeah. Are people likely to die from it? Probably not. Okay, because you can notice that there's a problem. You go to the office, and then they go like, oh yeah, there's something wrong here, and then somebody is going to fix it, right? Now think about Tesla today. Okay, what do you think Tesla makes? I know you guys know some of the answers, but not all of the answers. Tesla makes electric cars, right? But they also make electric rigs, the 18-wheelers, right? So, and they automate that. Okay, and Tesla is not the only company that automates 18-wheelers. There are many other companies who also automate 18-wheelers, even though those are still diesel-based and not electric. In other words, on the road now may not be in California, but in some other states, there are already 18-wheelers that are automated. Hmm? Sorry?
I saw one.
You saw one?
Driver, right?
Yeah. Yep. So think about, okay, so how can they get it done? What makes it possible for these 18-wheelers to be able to drive themselves? It's automated because of computers, right? So that means they're running some kind of a program, right? What if that program has a bug and it has a security exposure? Then people can hack into it, right? So most people think, oh, this is kind of cool. I can hack into an Amazon delivery truck and have it to drive to my driveway. Then I can empty out the Amazon truck and I'll get rich. Okay, well, that's small time thinking. Okay? Think about an 18-wheeler that is hauling gasoline, liquefied compressed propane gas, and stuff like that. Think about the consequence of a hacker who has really malicious intent. What do you think that person can do? Pretty bad stuff, okay? I'm not going to say it, okay, because I don't want people to get nervous about it, but pretty bad stuff, right? Forget about guns. Forget about line of sight weapons. This is far, far more dangerous. Because if the same hack to hack into one 18-wheeler can be used on all automated 18-wheelers running the same operating system and the same firmware. Does that make sense? So if you think about one, it's already bad enough. But if you think about the whole fleet, like 200-300 of these 18-wheelers, all over the country, that's big time security exposure. Another thing, what if the control software of a satellite is hackable? We're talking about a normal satellite, not a spy satellite or an attack weapon satellite. We are talking about the space station, okay, something like that, okay, something that, or the Hubble telescope, okay. It's not by itself a weapon. But what if someone can hack into the maneuvering rockets or the propellers, okay, so that they can just change the orbit a little bit. What would be the consequence of that? You can drop a satellite, exactly. And if you have fine control over those thrusters, you can basically say, I want that satellite to crash over here. Is that a bad thing? How destructive is that? Forget about the 300 trucks with gasoline. That's nothing compared to a satellite crash landing in a major city in terms of how much energy that's going to disperse. So as we automate more things, as more things are now becoming controlled by computers, the risk is also increased by a great deal. Instead of saying, oh, my paycheck is not right, okay, we can be looking at entire cities being leveled by a satellite. Now, if you're not concerned right now, I think you really need to think about this a little bit more, because all of these things are already in progress. Okay? So now the question is, how do we stop this? Because the idea of scaring you is to make you think about, oh, we got to stop this. I mean, this has to end. We cannot afford to have security exposure when it comes to satellites, when it comes to transportation, when it comes to the power grid and stuff like that. So how do we stop? How do we make sure that this does not happen anymore? In other words, how do we make sure that software do not have flaws anymore? How do you test software? Okay, so let's just say that you are the person who is in charge of the firmware on one of the satellites. Okay, so you are responsible for the communication hub that that can remotely control thrusters of a satellite or somewhere along that chain. Okay, so you write your stuff according to the specification. Okay, your boss gives you a specification and say, okay, when you receive this message, that should happen. When you receive that message, that should happen, and so on. Okay, how do you test it? Yep. Sorry?
You try hacking it yourself?
You can try to hack it in yourself. Okay, that's one thing you can do. But how do you do that? How do you try to hack into the program?
Or you get like white hackers.
So you can hire white hats. Okay, that's good. Okay, now let's just say that you do have a team of white hat hackers, and if you don't know what that term means, it means those are hired hackers. They are actually employees, and they are doing something that is legal because they were asked to hack into a system to see whether the system is secure or not. Okay, so yes, you can hire a team of people like that. Now let's just say that that team could not hack in. Is that any guarantee that there's no flaw in the system or that the flaw has not been discovered? How can you differentiate between those two? Yes? Oh, I thought you had a question.
Maybe check the post condition.
Pre and post conditions, okay? So how does that have anything to do with what I just said, the pre and post conditions? You're trying to mathematically prove that your program does what it is supposed to. So because it's a mathematical proof, you're not throwing test cases at it. You're not just trying to say, okay, I have a team of hackers, and we'll just keep trying to hack into the system. You're trying to prove mathematically, once and for all, conclusively, whether the program is hack-proof or not. Is that okay? If you can prove it, okay, if you can use mathematics step by step and use logic to prove that your program does exactly as specified and there's nothing wrong with the specification itself, then your system is secure. And you can just move on. You don't need to test it anymore. The approach of using white hat people or just to use test cases is kind of like this. You can just kind of imagine that this is a veil, okay, over the whiteboard, and instead of a whiteboard, we have some dots here. Okay, so let's say the black dots are representing places where your program doesn't work as expected, and some of these can turn into security exposures, but not all. Sometimes it just crashes. Okay, but because people cannot see those black dots, so what do? You throw dots at the projection screen. Okay, so you throw a dot at the projection screen, you remove the dot and say, is there a black dot behind this, this hole that I just poked? No, okay, no flaw there. Then what do? You throw a second dart. You pull the dot out and go like, do I see a black dot behind that? Nope, okay. So you check two places and there are no flaws, in these two places. Then you throw the third dart, the fourth dart, and so on. Let's just say that you throw 40 million darts and you have not yet seen a single black dot behind it, behind the screen. Does that guarantee the next one will not land on the black dot? No. Does it mean that there are no black dots behind the screen? No. So testing can never tell you conclusively whether there's a flaw with the system or not. It can only confirm what you have tested is okay. There's no flaw in what you have tested. But unless you can test every single case, then you cannot be conclusive. But when you're talking about a mathematical proof, then it is once and for all. Because it is mathematical, it is logical. So if you can prove that your program does what it is supposed to using a mathematical proof, then you don't need test cases anymore. You can just say, this just works. And then you can move on. Is that okay? Are we good? So this area of computer science is called automated theorem proving. Okay, so just in case anyone is interested, it's called automated theorem proving or program verification. Now, this is not a new concept, not at all. Okay, I remember when I was in college, which was a long time ago, it was already on the topic of of many discussions. But back then, people just go like, okay, one, we don't need to use this. Okay, there's no need. And then two, we don't have the computation power to do it either. Well, both of those statements are no longer true. Okay, because now we do have a need. Okay, cybersecurity is just as important as any other form of security, if not more. If you think about it, it is actually more important because without cybersecurity, you may have the best weapon hardware. But if any other country can hack into your weapons, they can turn those weapons against you, which makes you think which makes you think you wish you had inferior weapons, right? Instead of these, super duper whatever missile and guns, I would settle for a water gun. So if it gets hacked, I just get water. Is that making any sense? Why cybersecurity is actually super important, even though it's not glamorous. There's no explosion. There's no firework whatsoever. It is actually more important than anything else now. Okay. So now there's an interest to do this again. Okay, because now we have a need, we have the computation power, and we just need to keep working on it until we can get it done. We can achieve that. So that is the premise. That is the reason why this topic can be important in your career as a computer science, computer engineering, or electrical engineering expert. Is that okay? All right. So now that we have talked about the reason and the motivation of all of this stuff here, we'll kind of go in and talk about what is a precondition and what is a postcondition. Now, you already know the word pre because I asked you to use pre as the line number in a trace. Every time you start with a pre. And it does mean precondition, but that's the precondition of the execution of an entire program. When your program is done, when you're done tracing your code, I also ask that you label the last row in the trace as post, because you're basically telling me this is the post condition of executing this program. Okay, so but we don't have to use pre and post only at the very beginning and only at the very end of a program's execution. We can do it on a per statement basis. In other words, every time we execute a statement like this, we'll say, what is the precondition? It's that. What is the post condition? It's that. And then what is the precondition of the next one? It's that. What is the post condition? It's that. And so on. Now, in this class, we'll have a way to mathematically derive a post condition depending on what is the precondition and what the statement is, which allows us to theoretically prove what is the end result of executing a piece of code. Okay? And you look at this example and go like, oh, we can just trace it, right? If we can trace it and it's conclusive, why do we need to prove it? So this is a bad example. So instead of using the example that is already on the projector, I'm going to give you a different example so that you can understand what I mean when I say, well, sometimes, if you just look at the code, you do not know whether it is correct or not. Okay, so this code here we have seen already as well. I certainly hope that you guys recognize this, at least a little bit. Yes? What does it do? I claim that this code does a certain thing, right? So what did I claim in previous classes? It's not a loop. It stores the maximum of x and y in Z. Okay, that's what I claim. But how do we know that this works all the time? Remember I threw some test cases at it in a previous class? I threw a few test cases. One test case was x is the larger one. One test case was y is the larger one. And I might have one test case when x and y are actually the same. It seemed to work in all three cases, right? But how do we know that it works in general? We don't. Okay? By throwing test cases at this code and checking the result of those specific test cases is no proof that this code is going to work all the time. Yep.
But what if you test every possible outcome of each statement?
Well, how many outcomes, how many cases do we have? How many values can x assume? X is an integer, and so is y. So x can assume, so In the case of actual programming, yes, there's a limit of what is the range of x, and there's a limit of what is the range of y. But you're testing a lot of cases when a proof can also give you the reassurance that this code does work all the time. So because this code is so simple, it only involves two variables and they're integers, we can actually test out all the possible cases. Okay, it's still a lot of test cases, but we can do it. If you consider x as a 64-bit integer and y as a 64-bit integer, the total number of test cases will be 2 to the power of 128, which is a lot. Okay, but it is still a finite number, and someone can argue and say, well, we have all these computational power, we can do it. Yes, but we can also use the same computational power, hopefully, to use mathematics to prove that this works all the time. Okay? So we'll just take a look at this code and see if we can analyze this. Okay? So I'm going to say pre1 equals to true. Now, what the precondition is this is a condition that is guaranteed to be true before a particular line executes, or immediately before that line executes. So when I say pre1 is true, I am saying that when line 1 executes, the condition true is true. And no one is trying to point out, but tech, that's saying nothing. To say that true is saying nothing. Yep. Say that one more time.
In what case would a precondition before it begins executing false?
We'll see some cases like that. Those will be the cases when we have what we call a dead branch. But we are not dealing with a dead branch at this point yet. Okay. But to say that true is true, does it have any actual meaning? Does it tell you anything about x or y or z? Nope. But that's the whole point. I'm not making any assumptions. I'm not saying, oh, let's assume x is 1 and y is 2. No. I'm not assuming that y and x are the same. I'm making no assumptions. Is that okay? Yep.
But wait, when you say like true, do you mean like that the condition is true, so you go to the second one?
No, it is simply saying that the condition that is true prior to the execution of line 1, and that's even before we evaluate whether x is greater than y. Okay, so that's a good question. So pre1 is identifying a condition that is true before the execution, immediately before the execution of the line that is in the parentheses. So pre1 is true is saying immediately before line 1 executes, we know that the condition true is true. And if you are thinking in your head and go like, tech, that's saying nothing, you are absolutely correct. That's exactly the intent of this precondition, is to say assume nothing. Yep.
That's just basically agreeing with the true condition.
It is the same as.
So it's just agreeing with the true condition, saying that whatever we get that is true is actually true.
No, it is just saying that, okay, if a precondition of a line is false, that means that line would never execute. Okay? So if I say pre1 is true, it simply means, yeah, we start with line 1, but I'm not making any assumptions about x or y. Okay? So that's basically what this line is saying. Okay. If that is the case, can I say something about line 2? So remember the context, the semantics of pre2 is line 2 is about to execute. But right before line 2 executes, what do I know to be true? Okay, so I got a few answers. So raise your hand if you have an idea. Go ahead.
I think x should be bigger than y.
X is greater than y. Yep. Same. Okay. So instead of just writing that, I am going to write this. Now, I understand that this is not saying a whole lot, but whatever pre1 is still true when line 2 is about to execute. because between line 1 and line 2, there's no code to change the value of any of the variables. So whatever is true right before line 1 has to still be true right before line 2 executes. So I use it like this. But since we are already told that pre1 is true, then it becomes true and x is greater than y. Okay? Are we okay with this statement? Because, because we make the assumption that pre1 is true, then we can also say, because pre1 is over here, we can now say that, pre2 is really just true and x is greater than y. Is that okay? Yep.
So pre-2 is basically just telling us things we already know, right?
Pre2 is telling us what condition has to be true right before line 2 executes. And we know that right before line 2 executes, x is greater than y has to be true, because otherwise we wouldn't be there. Is that okay? Yep.
Back to the pre-1 real quick. You said we're not making any assumptions about the variables, but we're assuming that the condition is true.
Okay. I have to come over here because I couldn't hear you.
Okay, for pre-1, you said we're not making assumptions about the variable, but we are assuming that the precondition itself is true.
Are you talking about the precondition of line 1 or line 2?
Of line 1,
Of line 1, yes. We are assuming
the precondition is true.
no. We are saying that true is true.
Okay.
So the precondition is true. Okay, so let's go back and talk about what is a precondition. A precondition is a condition that has to be true prior to the execution of a line. Okay? So it can be anything. I can give you some really random condition that is true and just say that, well, okay, text says this has to be true before this line starts executes. Okay? But in this case, I'm saying, well, I'm not making any assumptions. So the only statement I can make is true is true.
Okay.
Is that okay? Yep.
Isn't that the whole point of an if statement?
It is the whole point of an if statement. Yes.
So why are we adding the pre stuff?
We'll see why in just a moment. Okay. So we'll finish this today. All right. Can we simplify this to simply x is greater than y? What do you think? And if you're nodding, how do you know? In other words, the question really boils down to, if I have a variable x that can either be true or false, when I say true and x, what is the value of that conjunction? Okay, since x is a Boolean, what value can it store? True, false. Okay. So it can be true, it can be false. Okay. When x is true, what is true and true? True and true is true. Okay. When x is false, what is true and false? False. Okay, very good. Do you notice the two columns are exactly the same? True, false, true, false. So now we have established if you have a variable x or some expression x, true and x is really the same thing as x. It doesn't say any more than that. Is that okay? So this is what allows me to simplify from true and x is greater than y to just x is greater than y. You can look at true as 1 and the conjunction as multiplication. X is the same thing as 1 times x. It really has the same connotation here. Okay. So if that is the case, if this is how we can analyze the precondition of line 2, what about line 4? If I am about to execute line 4, I'm right there, just about to execute line 4, what can I tell, what has to be true if I'm already at that place? What is false?
Line 1.
No. Pre1 is still okay. There's nothing wrong with pre1. Pre1 is still true. But what has to be false? The condition of the conditional statement has to be false. Okay. So this becomes pre1, because remember, when we evaluate the condition on line 1, if it is false, we go straight to line 4. So whatever was true when we are about to execute line 1 has got to still be true when we are about to execute line 4. But on top of that, we also know something else. Because the only way to get to the else branch in a conditional statement is for the condition itself to be false. So we know that x is greater than y has to be false when we are about to execute line 4. So the way we say this is and not x is greater than y. So we'll go ahead and simplify this a little bit. Is that okay? Is everybody buying this? It is not the case that x is greater than y. It's really saying the same thing as x is less than or equal to y. X and y both being numbers. Can we buy that? Okay. And then we can simplify it one more time. So we can now simplify it to just x is less than or equal to y. Would that be okay? I'm using the same trick to get rid of the true and out of the expression. Are we good? Okay. So far we haven't said anything about z. In other words, I did not assume anything about z, but so far I still don't know anything about z. Does that make sense to you? Makes perfect sense, right? At this point, I have not executed a single assignment statement yet. And without a single assignment statement, and z starts with an unknown value, it remains unknown. I still don't know what it is. Okay? So the next line here is to analyze. This is going to get a little bit interesting. What is post 2? In other words, this is the condition that has to be true immediately after the execution of line 2. Okay? What has to be true? Yes? Sorry? X is still greater than y. Okay. What makes you think that still has to be true? Because x is not being changed. Y is not being changed on line 2. If x retains its value, y is retaining its value, and x is greater than y before line 2, then x is greater than y has to be true after line 2. Is that making any sense? Because line 2 does not change x nor y. But don't we know one more thing now that we did not know before? What does line 2 do? It updates z, but we also know how it updates z, don't we? So x and z are now the same. Yep. There we go. So likewise, we can try to come up with a post 4. What do you think post 4 should look like? Post 4 is representing the condition that has to be true immediately after line 4 executes. And line 4 is right here. And this is pre 4. So post 4 has to do with pre 4. Okay, it is related to pre 4 in some way. Yep. Yep, exactly. So now we know that x is less than or equal to y, and y equals to z in this case. Okay, so we're almost there. Now, in a normal trace, we do not trace line 5 because line 5 has no meaning when it comes to what does it do. But when we analyze pre and post conditions, we do want to know what is post 5. In other words, if there are other things after line 5, what do we know to be true when we just start on line 6, if line 6 has something? What do we know? Now this one is a little bit tricky. So what I'll do is I'm going to draw you a map first, and then you guys can tell me what you think is the answer. The reasoning of everything that I'm talking about is in the notes already. Okay, so focus on what I say and don't try to spend all the time copying. So I'm going to use Zernal and open a new page. Here we go. All right. So the first thing is I'm going to draw you a picture of a conditional statement, okay? And I'm certainly hoping by now this does not look foreign at all, okay? So we got two places. They merge back like so. And every time you have a split, in other words, you have two ways to proceed, there's always a condition that you have to answer. There's a question you have to answer. So in this case, the question is, x is greater than y. If it is true, you go this way. If it is false, you go this way. If you go to the left-hand side, then z gets the value of x. If you go to the right-hand side, z gets the value of y. Okay? So are we agreeing that this picture represents the logic of the code that we are just talking about? Oops. There we go. Is that okay? Okay. Where is line 1? What does pre-1 mean? Pre-1 means right here, right at this point, when you're right at this point on the trail, what do you know is true? Well, since I don't make any assumptions about x or y or z, all I can say is, well, true is true, because I don't want to say anything about the variables. Yep, go ahead.
So you just assume line 1 is true, but you don't know anything about it, so you just assume it.
Hmm?
So pre-1 is just you assume that line 1 is true. You don't look at
Not so much line 1 is true, but the condition that has to be true before line 1 executes is true, which is not saying anything. Okay? That's also the whole point. So this is what our pre-1 is. Yeah, go ahead.
Your analogy to condition 1 is just assuming you're walking down the trail.
Yes. So we are walking down the trail, but this is an interesting trail because it has a branch.
We just haven't gotten to the branch yet.
Sorry?
We just haven't gotten to the branch.
We have not gotten to the branch yet. Yes. So where do you think is pre-2? Pre-2 is right here. In other words, you woke up and you found yourself to be here. Okay? And you have no recollection of how you got there. The question now is, well, since you're here, what do you know that has to be true? Well, because I'm here, and the only way for me to get here is the answer to this question is true. So you know that x is greater than y when you're already here. Is that okay? So that makes this part here pre-4. Is that okay? This whole thing that we are doing here, this is what line 2 is. And this whole thing is, this is what line 4 is. Is that okay? What about post 2 and post 4? This is post 2. And this is post 4. Are we doing okay so far? Mapping the concepts, on the left-hand side to the picture on the right-hand side. Okay? So you have to remember, you kind of have to imagine that, while you are walking through this maze, you got drunk. Okay? You just woke up at a certain place and go like, I don't remember how I got here, but since I am here, how can I use logic to determine what has to be true at this point? That is the whole point of pre and post conditions and how we derive stuff. Okay? So post 5 is at a very interesting place. Post 5 is asking here. In other words, Tech drank something or ate something, okay, totally passed out, and then woke up here. If I'm here, what can I say that has to be true? One of them. Okay, so that's a very interesting statement, because when you say one of them, I can interpret it two ways. I can interpret it as one and only one of them, or at least one of them. Which one do you mean? At least one of them. Very good. Okay, so you got it right. At least one of them. So when I get to here, so I woke up here at post 5, okay? Somebody told me, oh, post 2 is this, okay? And somebody told me that post 4 is that, okay? That we have already derived. And then I woke up and go like, but I don't remember which way I came from, okay? Then the only answer, the only thing I can actually say for certain is post 2 or post 4. If I'm here, then the condition that is guaranteed to be true is post 2 or post 4. Does that make sense to you? Because I could have come from the right branch, then post 2 would be true. I could have come from the left branch, or I could have come from the right branch, in which case post 4 is true. But if I say post 2 or post 4, that means if post 2 is true, then post 5 is true. If post 4 is true, post 5 is also true. Well, that kind of meets all the requirements that I need. Okay, so let's go ahead and write that down. So post 5 is technically post 2 or post 4, and that has to do with the branches merging together. So, in other words, this has nothing to do with the code, the specific code here. It simply has to do with this is the merge point of the then and the else branches. Okay? Now, specific to this case, now we can substitute what we know about post 2. So what we know about post 2 is x is greater than y and x equals to z. What we know about post 4 is x is less than or equal to y and y equals to z. So now we have a conclusion. In other words, assuming absolutely nothing about x or y, I can come to this conclusion and say, by the time we're done with this conditional statement, we know this has to be true. X is greater than y and x equals to z, or x is less than or equal to y and y equals to z. I think that is pretty cool, considering that I did not make any assumptions about x, y, or z at the very beginning. But now the question is, but is that really saying the same thing as z is the maximum of x and y? Okay, let's think about that. Okay, so let me write it down so that you can see what I want you guys to be thinking about. What does that mean when I say x is the maximum of x and y? I mean, I know you guys what it means, but if I want to boil this down to just comparison, conjunction, disjunction, and negation, how would you express it? So let's give it a few tries, okay, and see if it works. Okay, so can I, instead of saying z is the maximum of x and y, can I just say that z is greater than or equal to x and z is greater than or equal to y? Is that saying z is the maximum of x and y? Are they equivalent expressions? Okay, let's run a few scenarios through, okay? Let's just say that x is 1 and y is 2. Easy enough, right? So most of you will say, oh, so that maximum is just 2. What if I say z is 5? Z is 5, okay? 5 is greater than or equal to 1. True. 5 is greater than or equal to 2. That's true too. True and true is true. And yet, that is not how we define maximum, is it? 5 is not the maximum of 2 and 1. What am I missing? I mean, this is good. It's a good starting point, but it's missing something. What is it missing? The maximum has to equal to at least one of those two variables. I'm missing that one extra constraint. Okay. So now we can say, fine, we have to, we have one more condition that we have to satisfy, which is z equals to x or z equals to y. It has to equal to at least one of those two. Can it equal to both of them at the same time? Sure. If x is 2 and y is also 2, then z equals to both of them. Okay? So I just need at least one of those two, and it will make it happy. Is that okay? So now we have another question. It's basically saying, is this expression here saying exactly the same thing as this expression here? Are they equivalent? They seem to be equivalent, right? But can we prove it? Now, I'm not going to ask you guys to prove this because this would be the kind of stuff that you need to do in CISP 440, discrete structure. So in this class, I'm not going to ask you guys to prove this. I will walk you through the proof in the next class, okay? But the idea is, yes, once you know how to use Boolean algebra, you can actually prove that this expression here is exactly the same as this expression here, which we accept to be equivalent to z is the same as max xy. So skipping that step of proof, yeah, go ahead.
So if we're doing like a pre and post condition, we stop at post 5, right?
Yes. Well, in this case, because that's the entire program. Yep. But the point is, okay, so let's just assume that I have already gone through the formal proof using Boolean algebra that this statement here, or this condition here, leads to this condition here. They're exactly the same, which establishes z is the max of xy. Okay, so let's assume that is already done. Okay, and then can we be conclusive that this code works all the time?
If it's proved, yeah.
Yep, exactly. So if I can bridge these two expressions, then I would have proven that this code does find the maximum of x and y and store the maximum into z. I don't need to test it anymore, not even a single test case, because I have conclusively, using logic, to prove this works all the time. You can give me any value in x, any value in y, I will still find the maximum and put that maximum into z. Now, I understand this is a very simple piece of program. It doesn't do much. It just finds the maximum. But that is the idea. Okay? So now you can think about, okay, I know we are running out of time, but you can think about we scale this up. So instead of working with a 5-line piece of code that is really simple, we apply the same technique to the SSL library, which basically was the source of the heart bleed bug. Okay? And we come up with an expression that is long, huge, but it does match what the code was supposed to do. Then we would have conclusively proven that that piece of code does exactly and only what it is specified to do. Not more, not less. Exactly. This is what we want to do to at least crucial parts of an operating system, crucial parts of the TCP/IP stack code, so that key pieces of the operating system can be known to be trustable. It works. We know it works all the time. Okay. Now, does it mean that your phone won't crash, or your Fitbit won't stop working in the middle of the day? No. We are not going to do this to every single piece of program, but we only do it to the crucial parts. Okay, if you think about it, if an 18-wheeler that is automated just decides, I'm just stopping in the middle of the nowhere because my program is not working anymore. Does it do a lot of harm? No, not really. I mean, well, whoever is supposed to be receiving the goods, is not receiving it. That's the only harm. But it's not nobody has control over it. So crashing is not as much of a big deal as being hacked, because being hacked means someone who is not supposed to have control over this piece of asset now has control over that piece of asset. Okay, now, just one more thing, just so that you guys have one more thing to think about and talk about when you get home, is, do you think military drones are now automated? Okay, I think most of you have watched news footage of, oh, look at these people sitting in a bunker, flying drones remotely halfway around the world. You have seen those footages, right? There are many movies with that as well. So the question is, are drones manually controlled now, or at least in the near future, or are they fully automated? They are becoming fully automated.
But what if someone hacks like an attack drone?
That's a very good question. And I don't think anyone wants to know the answer, or the answer is not going to be pretty. So I will leave that in your thoughts, okay, over the weekend. But read the module. I know it is dry and boring, but it is really important to read it over the weekend. And then on next Tuesday, we are going to come back and dig at this stuff here.